Hi, this is Dane Quinn from the University of Akron, and today I'd like to do another example modeling equations of motions with Lagrange's equations. So here's the system that we'll look at. We have two disks, right? We have a small disk that is grounded with a spring and a damper, and then connected with a cable to a larger disk. The stiffness of the cable is K in both cases, and the damping coefficient is B. Notice that this larger disk is twice the radius and 4 times the mass as the smaller disk, and the cable connecting the two is attached to the center of the larger disk and then wraps around this smaller disk. So let's start off, and as we always do, think about the problem. So this is a 2 degree of freedom system. We need 2 coordinates to describe the configuration. For example, we could use the angular rotation of the 2 disks. We could use the position of the center of the 2 disks. We could use some combination of that. We could look at the relative displacement. There are lots of different coordinates that we can use, but ultimately we need 2 to specify where this system is. And again, these disks roll without slip. So there's a constraint relationship between their rotation and translation. So now let's go and look at the disks themselves and identify the forces that act on them. So we'll draw the larger disk, and then maybe we'll draw the smaller disk down here. Okay, so what forces act? Well, we have the weight, we have the normal force, and we have the friction force acting on both disks. So normal and friction. And so we'll say this is W2, this will be object 2, N2, and the friction force acting on the second, and label those accordingly. Now let's look at the forces that arise from the springs and dampers. So on this left disk, on the smaller disk, we have a force that arises again from the spring and the damper acting on its center, and here we'll identify this as a spring force plus a damping force, and this is Fs1 and Fd1. Then we have force acting on the upper edge from this second set of springs and dampers, right? And this will be Fs2 and Fd2. So again, the second spring, second damper. Now, this force is an internal force, right? So whatever acts on the left disk also has to act on the right disk. And the force has equal magnitude and opposite direction. So we'll write that as minus Fs2 and Fd2. So these are the forces that act on the system. Now, the spring forces are conservative. So they will be included in the potential energy. The damping forces are non-conservative. They will be included in the generalized forces. Finally, the normal and frictional forces those are constraint forces. They impose the no slip condition and the fact that the disk can't move through the surface. So they're constraints. They do no work, and they don't enter into Lagrange's equations, except through the kinematic relationships. Finally, we have the weights. Right? Here, because the disks don't change height, while these weights are conservative, they also do no work. So I can actually leave them out of the formulation. Again, just like the normal and frictional forces, they don't contribute work to the system, and so they don't enter into Lagrange's equations. Again, they are conservative, but here the surface is horizontal, and as a result, they don't change height. So, because of the damping forces, and in particular the damping forces being non-conservative, right, the system as a whole is non-conservative. So again, we will have to go through and calculate the generalized forces that are associated with these damping forces. The spring forces obviously will be included in the potential energy. So let's start off and define coordinates. Right, so here we'll use directions I and j. And what coordinates can we use to describe the motion, as well as the forces and potential energy? Well, let's look at the motion of the disk first. So here, let's define the rotation of the disk, particular disk 1, as theta 1, and the rotation of disk 2 as theta 2. Then we'll look at also the displacement, the translation of the center of the disk. I'm actually going to draw this point slightly over there, just to indicate that every point on this part of the cable has the same displacement. Right, so here, let's define that displacement as x1. And for the second block, again, I'll do the same thing. Every point on this part of the cable has the same displacement. So we'll define that as x2. So notice that the displacement of the center of the disk is exactly x2. Again, displacement means the difference in position from its starting point, right? So each of these 2 points moves the same amount. Now, so we've got the relationships, or we have coordinates that describe the motion of the objects, and of course these are constrained, right? So here x1 is equal to minus r theta 1, and likewise x2 is equal to minus 2r times theta 2, because again the radius of this disk is twice the radius of the smaller disk. So then we go and look at the forces. Well, this spring, its stretch is precisely x1. Now, the force in this connecting spring depends on the displacement across the spring. Unfortunately, x1 nor x2 nor either of these other rotations explicitly gives us that. So let's define a new coordinate that describes that relative displacement. So we'll mark a point here on the left, and we have a point on the right, and as a result we'll call the relative displacement across that spring as z, which means actually that we also need to know where this point is on the left. So we'll define a coordinate there, call it y1, that describes the absolute position of this. So now we have some extra constraints. Right? In particular, looking at y1, we can go through a simple kinematic analysis and show that y1 is 2r theta 1, well, minus 2r theta 1, which actually ends up being 2x1. So this upper point moves twice the distance of the center of the disk. And then finally, looking at this relative displacement, we see that x2, so the displacement of the right, is the displacement of the left, which is y1, plus the relative displacement between those two, z. So now we have 1, 2, 3, 4, 5, 6 coordinates and 4 constraints, again giving us a 2 degree of freedom system. So if we look at the kinetic energy now, each disk rolls without slip. And it rolls without slip on the ground. So, in such a case, if I have a disk, this could be either disk in this case. Let's say G is the mass center, and here O will be the contact point. Then we've shown that the kinetic energy is 1/2 times the moment of inertia about the contact point times theta dot squared, where theta here is the rotation. So this encompasses both the kinetic energy due to the translation of the mass center, as well as the rotation of the disk as well, defined by theta. Now, if this disk has radius rho and mass capital M, and I use those to distinguish from the mass or the radius of these two disks, then we find that I.O. is 3 times the mass of the disk times the radius squared divided by 2. So now the total kinetic energy is just the sum of the kinetic energy of the two disks. And so we can use our relationship here and here to determine that. So for the smaller disk on the left, it's 1/2 times 3mr squared over 2 times theta 1 dot squared. For the larger disk, it's 1/2 times 3 times the mass. Well, remember the mass was 4m, and the radius was twice r, so 2r squared divided by 2, theta 2 dot squared. Or, kind of simplifying this, 1/2 3mr squared over 2, theta dot squared, plus 1/2 times, well, this works out to be 24 mr squared, theta 2 dot squared. So now we turn to the potential energy. Well, again, the total potential energy is just the potential energy of all the parts. So here, that's spring 1 and spring 2. So we have potential energy in the first spring and the potential energy in the second spring. So looking at these springs, we have 1/2 times the stiffness, and so we'll look at the spring 1 first, times the displacement or the stretch in that spring, so that's x1 squared. And then for the second spring, we had 1/2 k, and the stretch was defined as z squared. So the total potential energy is just the sum of those two. So finally, the Lagrangian is simply T minus V. So the total kinetic minus the total potential. Right, so in terms of what we've written, The kinetic energy was given here. So that's 1/2 times 3 mr squared over 2 theta 1 dot squared plus 1/2 24 mr squared theta 2 dot squared minus now the potential energy 1/2 kx1 squared and 1/2 kz squared. Now, to apply Lagrange's equations, we need two independent generalized coordinates because it's a 2-degree of freedom system here. Notice that we actually have used 4 coordinates in this description of Lagrangian. So I need to go through and figure out, or basically just choose 2. Right? So let's choose x and y, or x1 and x2. Right, so here, theta 1 was equal to x1 over r. Theta 2 is x2 divided by 2r. And then finally z we found to be x2 minus 2x1. So, using these constraint equations in the Lagrangian, we find that L reduces to the following. And again, it's t minus v. It's 1/2 times 3m over 2 times x1 dot squared, right from here, plus 1/2, and now this becomes 6m x2 dot squared minus k over 2 x1 squared plus 1/2 k times z, which was x2 minus 2 x1 squared. So this is now the Lagrangian written in terms of our 2 independent coordinates. But we're not ready to apply Lagrange's equations yet because we still have these damping forces. So now we need to go and determine the generalized forces. So let's find the generalized force associated with x1 first. So remember how we do that, right? Essentially, we take x1 and increment that with a virtual displacement delta x1, while we leave x2 alone, right? x2 stays where it's at. So now, if I look at these forces, and here, this force was FB1, and it's going to be minus B x1 dot in the I direction. Right, so remember I was this direction and J was that direction. While for this second force, FB2, that's B times Z dot in the I direction. So acting on the larger disk, that force is minus FB2, which is minus B Z dot in the I direction. And so actually I'm going to gray these out because it's these quantities in blue that we're really interested in. So the force acting on the left disk, minus bx1 dot, and then plus bz dot, and minus bz dot in the I direction is acting on the larger disk. So when we increment these virtual coordinates, I need to find out how much these forces are displaced. Right? So let's call this point A, and we'll call this point B, and we'll call this point C. So this force acts at A, and I need to determine how much A moves. Well, if x1 is incremented, then A moves by the same amount. So delta x1 in the I direction. Likewise, if delta x1 is incremented, then b moves twice that amount. Because remember, y1 is twice x1. So the increment follows the constraint relationship. And then finally, point C, that doesn't move at all, right? Because x2 is held fixed, right? So there's no increment on C. Alright, well now I can go and calculate the virtual work. It's just this force, B1, dot the displacement, plus the next force, B2, dot the displacement at B, and then finally plus the third force, which is minus FB2 dot delta R, C, the virtual displacement of that force. And so this works out to be the following: minus B x1 dot in the I direction dot delta x1 I, and then B z dot in the I direction dot 2 delta x1 I plus 0, because while this force is non-zero, delta RC vanishes. So as a result, the virtual work done can be written as minus B x1 dot plus 2B z dot times delta x1. So this is qx1, and it's just minus B x1 dot, well, plus 2B z dot, except z, remember from our constraint relationships, z dot is equal to x2 dot minus 2x1 dot. So we will use that there. So this is my generalized force, and notice that these two terms combine, so we would actually have 5b x1 dot plus 2b x2 dot. So that's the generalized force for x1. Now we need to do the same thing for x2. So we're looking for qx2 now, and here we will hold x1 fixed, and we increment x2 by an amount delta x2. So again, just like I did before, this is point A, that's point B, that's point C. Now the displacement of A is equal to 0 because x1 remains fixed. There's no virtual displacement. And so the virtual displacement of B is 0. And the virtual displacement of C is exactly delta x2 in the I direction. Once again, these forces are minus B x1 dot in the I direction plus B times Z dot in the I direction, and then minus B Z dot in the I direction. So we're ready to go and find the virtual work. Minus B x1 dot in the I direction, dot 0 because delta RA is equal to 0. For the second force, again, that vanishes because delta RB is equal to 0. And then we have the third force, which is displaced by delta x2 in the I direction. So the total virtual work is minus B times Z dot, need a dot there, delta x2. And As a result, this is qx2, which is minus bz dot. And again, I'll write that up here, x2 dot minus 2x1 dot. So we end up with minus b x2 dot minus 2x1 dot, or 2b times x1 dot minus b x2 dot. So finally, we're ready, right? So this is our Lagrangian, and I will also write out the qx1 is equal to minus 5b x1 dot plus 2b x2 dot, and qx2, and this was found from the previous slides, 2b x1 dot minus b x2 dot. Right, so to evaluate Lagrange's equations, right, we have to calculate a bunch of partial derivatives of the Lagrangian. Right, that's fairly straightforward. Partial of L with respect to x1 dot. Right, looking at this term in particular, we just get 3m over 2 times x1 dot. And the partial of L with respect to x2 dot becomes 6m x2 dot. Then the partial of L with respect to x1, and this minus sign here I'll put over on the left, is kx1 plus k2 or x2 minus 2x1, and now times the derivative of what's inside with respect to x1, which is minus 2. Finally, the partial of L with respect to x2 is k x2 minus 2x1. So now we'll just apply Lagrange's equations. Remember, we take the total derivative of this, so let's do x1 first. We'll take the total derivative of this term, so that gives me 3m over 2 times x1 double dot. Now this term, and I'll go ahead and combine these x1 pieces, so I have 5k x1 minus 2k x2 equals qx1, right? So that's minus 5b x1 dot plus 2b x2 dot. And then for the second equation, we get 6m x2 double dot plus, well, actually we'll start off with the x1 term, minus 2k x1 plus k x2 equals 2b x1 dot. So this is the qx2 term. And these are the equations of motion. But let's go ahead and simplify these and write them in matrix form. So here they are again, right? This was the equation from x1, and notice that I moved these damping terms over to the left side. And this is the equation for x2. Again, I moved these damping terms over to the left side. So in matrix form, we have the following. Well, 3m over 2, 0, x1 double dot, x2 double dot. So this is my state vector. And this will be my mass matrix. The damping vector will come, or the damping terms will come next. Now we have 5b and minus 2b x1 dot x2 dot, And then for the stiffness terms, we actually have 5k minus 2k. x1, x2. And then this equals 0. For our second equation, 0 and 6m, we have minus 2b and just b minus 2k from here, and then k equals 0. So again, this is a damping matrix, and x dot. This is our stiffness matrix, x. So in matrix form, mx double dot plus cx dot plus kx equals 0. So that's it. That's a nice modeling example dealing with disks that rotate, some relative motion between the two. I do want to point out that you may notice that the damping and the stiffness matrix look very similar. Right? In particular, just take K here and replace it by B, and you get the damping matrix. So, in general, that's not true. It is true in this specific example, right? And really, it's true because if I look at the springs and the dampers, they always appear in parallel combinations, right? So, if I have a K, that appears in parallel with a B term. And again, here, I have the same group of elements. I have stiffness and damping, and they always appear together, and in particular with the same values, or at least the same ratios between stiffness and damping. So in this specific example, the damping and stiffness matrices look similar. But again, in general, that's not true. So I just want to point that out in this problem. So again, that's a nice example, and thank you very much. I will talk to you again. Bye.